Right, so we could also talk about the energy. Some reactions, if you remember back to our chapter on energy, we talked about exothermic versus endothermic reactions. Was that it again? Okay, that was a lot of things. I didn't hear any really. But yeah, so exothermic reaction, heat is released, so heat transfers from the reaction to the surroundings. And endothermic reaction is the opposite. Heat transfers from the surroundings into the reaction. So you have to give it heat to go. How do we experience an endothermic reaction? What does it feel like? Endo.
Wouldn't it just do ice melting?
Yeah, but that's true. Ice melting, so it's taking in heat, although if it's in a chemical reaction, usually we experience that as being cold. So if something feels cold, what?
Or it goes from boiling to cold?
Well, if it's a chemical reaction, not a phase change, meaning that it's like taking in, like we did that one reaction in lab, where you dissolve the stuff and it got cold, that's an endothermic reaction. An exothermic reaction gets hot if it's a chemical reaction. So sometimes when we want to talk about that, we do it in graph form. So we can draw a graph to plot the energy versus the reaction progress. So as the reaction goes from beginning to end, what is happening with the energy of the stuff in the reaction? So one type of reaction might look like this. The reactants might be at this energy level, so they have this much potential energy inside them. And then the products might be at this level. And does this represent a loss of energy or a gain of energy going from reactants to products? A loss, because they started with more energy and ended with less energy. So that's an example of an exothermic reaction. It has released its heat. Remember, energy isn't created or destroyed. So it's not like the energy just ceased to exist, but it was transferred. It left the reaction and went out to the surroundings. We draw a little curve that looks like this that shows that progress. And that hump in the middle is important. So this is an exothermic reaction. And the reason we draw that little hump instead of just a straight line from reactants down to products is because there's another part of the reaction that is this difference in energy. And that is called the energy of activation, or the activation energy. Yeah, that distance in energy, the difference between the reactants and that peak, is the amount of energy that you have to put in just to get the reaction to go. So an example of this is like burning fossil fuels, like natural gas in a Bunsen burner, or gasoline in your car. That's a very exothermic reaction, but it doesn't just happen on its own. You have to do what?
Physically change the state.
Well, no, let's say it's a gas. So you hook up your Bunsen burner to the gas.
You have to get heat.
You turn the gas on, the gas is flowing, but that gas is not combusting yet, right? It's just flowing. So what do you have to do to get it to start combusting?
Increase the heat.
Yeah. How?
Turning up the Bunsen burner.
No, it doesn't have a flame yet. It just has gas flowing through it. How do we get the combustion to start?
More gas.
I don't think we're thinking about the same thing. So you take your Bunsen burner out of the cabinet, you hook it up to the gas, you turn on the gas. Right, you need a spark. So that's your activation energy. You need to put in energy by sparking it or heating it. That's what a spark is, right? It's just a bunch of energy. And that allows the reaction to continue. Now, you don't have to keep putting in sparks because the reaction overall is giving off a lot of energy. And so that makes it continue. But initially, you need that activation energy. All right, so the opposite is an endothermic reaction. And how is that going to look different? Right.
Wouldn't it go up since that graph shows it peaked with the energy activation, but then it went to a decline with the product?
Sure, I guess it depends on which way you're looking at it. Yeah. So it's going to be opposite, however you look at it, it's going to be the opposite. So
Because there was a loss of energy with the first graph.
right.
There's going to be
So there's going to be an increase of energy here, and that's an endothermic reaction. We still have the reactants on the left, the products on the right, and the path they travel through the reaction is given here. And so you see that the energy of activation here, we'll call it EA, energy of activation, is much greater, but it doesn't have to be. Different reactions have different activations energies and different whatever, but this is an endothermic reaction. The other important difference is the difference in energy between the reactants and the products. That's known as the heat of reaction. So that's the amount of heat that is either taken in or given off. In an endothermic reaction, that heat is taken in, is absorbed. In an exothermic reaction, right, here's the heat of reaction for that exothermic reaction, the heat is given off. The difference in energy between the reactants and products is that heat. And so we can actually calculate how much heat, we're not going to, but in here, but we can calculate how much heat is given off because we can measure the potential energy of the reactants and the potential energy of the products and just subtract. And then we'll know exactly how much heat is either has to go in or is given off.
The product is the right side of the graph, right?
Yeah, so the reaction always proceeds from left to right. Yep. And that's the way that we can look at the energies. Now, one important part of reactions, especially biological reactions, is something called a catalyst. You know what have you heard that word before? It's a word that's used outside of chemistry context as well, but it has a specific chemistry definition. Can anybody define it in any way at all? What is a catalyst?
Like an enzyme.
Yeah, so an enzyme is a good example of a catalyst. What does it do? Mm-hmm. Yeah.
Does it kill off something to form a bigger?
Maybe. Sometimes. A catalyst is actually anything that lowers that activation energy. And lowering the activation energy increases the rate of reaction. So the rate at which the products are formed gets increased. So it lowers that hump in the middle. If this is your normal reaction, your normal non-catalyzed reaction, your catalyzed reaction gives you a lower activation energy. And I put a couple extra humps in there because the way that it does that is by allowing the reaction to proceed but via a different mechanism. So you can imagine, like say you want to get to the other side of a hill. You can go up the hill and over the hill, or you can go around the hill. Right? The catalyst is like going around the hill. It gives you a different route that doesn't take as much energy to the same destination. And so this allows reactions to proceed in much milder conditions. And a classic example of that are enzymes. Enzymes are molecules in your body, usually large molecules, proteins, that accomplish various small tasks in the chemistry of your body. So converting, this sugar to this sugar, or converting this molecule to this thing, or putting this amino acid with this amino acid, all the little biochemical processes that happen in your body generally don't just happen on their own. They need an enzyme to facilitate that, to give them a route without so much energy. A lot of those reactions would take super high temperatures if we tried to do them in the lab, but with an enzyme, we can do them at your normal body temperature. And so that's what they do. Other catalysts, we use sometimes metals to catalyze types of reactions. In your car, you have something called a catalytic converter, which takes waste gases from combustion in your engine that are pollutants, like carbon monoxide. Primarily, it takes carbon monoxide and converts it to carbon dioxide. That's a difficult reaction, takes a lot of energy to do, but if you have this catalytic converter, which has some platinum or rhodium inside it, some of these elements, it allows it to happen at a more reasonable temperature. So that's what catalysts do. Yes, and they're not cheap because they contain really expensive metals like platinum, rhodium, iridium, everything kind of in that bottom 70s quadrant there tend to be pretty rare and expensive. Did you recently have to get one of those replaced?
Yeah, 4.
4 of them?
4 replaced.
In the same car?
Yes. They have several, whatever, catalysts. They have several in the car, apparently.
In different places?
Yeah.
Okay. Yeah, that doesn't sound cheap. And so if they go bad, you won't pass your emissions tests. Because
like it goes back, it's not going to convert the carbon, carbon monoxide.
yeah, it does a few different things. It does that. It helps get rid of some of the sulfur and nitrogen compounds that come out of your engine, like sulfur dioxide and things that other types of pollutants. So it converts them to more benign products. And so if it goes bad, then when they check what's coming out of your tailpipe in your car, they'll detect those molecules that are supposed to not be there. All right, and that's catalysts. That means that we can move on. And talk about gases. The gases is chapter 8 in the new book. It's chapter 6 in the old book. And we're actually only going to do a small part of this chapter. We're just really going to talk about it today and then be done with it. We're not going to get into all the calculations involved with gases. There are ways you can calculate volumes and pressures and temperatures, and that's not part of what this class is about. So we're going to talk about gases, kind of like what we did in lab on Monday. What happens when you change things? What happens to other things? And that's really the goal of everything we're going to deal with gases in this chapter. So there are 3 major parameters that we talk about with gases. We've got volume, how much space the gas takes up. We've got temperature, the temperature of the gas, and we've got pressure. Now, volume and temperature we've dealt with already. We know we measure volume in liters or milliliters usually. Temperature for gases, we're going to really focus on Kelvin because it starts at 0 and it makes a lot of the calculations easier, but we'll also deal with, of course, degrees C. Pressure is the new one. We haven't dealt with pressure because pressure isn't really an issue with liquids or with solids. You can't pressurize liquids, you can't pressurize solids. They don't compress, they don't change their volume. I mean, you can smush them, but you can deform them, but you can't change the volume that they take up. So gases, you can. You absolutely can. And so pressure becomes a really important way of dealing with and measuring gases. All right, so what are some units of pressure? Anybody ever measured pressure before in anything? Anybody know a unit that pressure is measured in? None? What about your tire pressure? Does anybody ever check your tire pressure?
Oh,
What do you measure that in?
this is like something,
What? PSI. What does that stand for?
pressure.
No idea. It's actually pounds per square inch. And so pressure is a measurement of a force over a particular area. Pounds are a force because it's the force that a mass exerts on the earth due to gravity. So however many pounds I am, that's the force that I'm exerting on the earth. And what? How many pounds? Yeah. We could play a guess the weight game. I don't want to play that. That doesn't sound like fun. But anyway, however much I'm exerting on the earth, the force is always the same, but the pressure could change. Like if I'm wearing my fancy high heels with the really skinny heels, yeah, that I have, of course, I'm exerting a lot more pressure on the earth. What?
On the ball of your foot.
Well, that's true also, but if you can imagine, like, if you ever walked on soft ground in high heels, you can like sink in, right? Yeah, because you're exerting more pressure than you are in those flat shoes. It's the same force, you're the same weight, it's the same amount of force, but it's over a smaller area, and that makes more pressure. All right. So our standard measure around here is pounds per square inch, but of course that's not a metric unit, so we'll have to convert to some other units. What? Of course. We'll use pounds per square inch. So by the way, what should your tire pressure be usually, most cars?
20 to 30 or something? Or
Yeah, it
30.
depends on the cars, 30, 35. How often should you?
Season.
It depends on the season. We'll get into how temperature affects that.
Yeah, so what is it supposed to be in like the winter versus the summer?
Well,
Depends on the
if
car.
you notice, so where can you find your car's tire pressure? Also something we should know. Where is it listed? Usually? It's not on the tire.
No, you open
Because
your
the
car
tires
door.
have a range. Because the tires have a range of what they can be at. It depends on the car. Yeah, it's in the
If you
door.
open up your car door, it says it right by the panel.
Yeah, it's either on the driver's side or the passenger side. There will be a little sign on your door, and the inside of the door that tells you what the tire pressure will be, and it'll usually say cold pressure.
Versus hot pressure.
Right, and which means that if you want to set your tire pressure properly, you always measure it when it's cold. The reason for that, as we'll get into later, well, we saw this yesterday. What happens when you cool something down? What happens to the pressure? Yeah, and the pressure goes down. So if you're driving and your wheels heat up and your tires heat up, they're going to increase in pressure. And so you're not going to get it right if you're measuring hot pressure. Why do you need to check your tire pressure often?
Well, is that the thing that like, isn't that like a little like tool that you use and stick in?
Yeah.
It pops up.
Okay, that's, okay.
Yeah. Next time you're at a gas station or pass by an auto store or something, just pick one up. They're like $1. Check your tire pressure. Why do you need to have the right tire pressure?
Because you can blow a tire.
You can blow a tire. So a modern tire, if it's kept at the right pressure, it won't just fail. It usually won't just blow out. I mean, it's very, very rare that would ever happen. If you see somebody's tire blow out, it's probably that either they let it go too long and so it was worn down, or it wasn't the right tire pressure. So underinflated tires and overinflated tires can blow. Also, it affects your fuel efficiency, your fuel economy significantly. So you can save quite a few miles per gallon if you have your tires inflated properly.
So it saves you gas?
Why do you think? Think about it. You have to press the gas pedal to move your car. Well, it's common sense, really.
I don't know if it's
Press your
common
gas
sense.
pedal, yeah, to accelerate, to get your car moving. If you
Okay.
have inflated tires, you're not gonna go as fast as, it'll take you a longer time to get to
Right?
60 miles an hour than it would with someone.
I'm not sure it's noticeable, honestly. I don't think you can notice just from acceleration.
You can notice walking out to your car and seeing.
You can see it, but I'm talking about driving. If you push down the accelerator, I don't think you notice if your tires are flat or not. But anyway, so lesson from today, if you don't learn any actual chemistry, go check your tire pressure. Make sure you're driving on the correct pressure tires. That's important, probably more important than this, so, for being honest. Let's save this. All right, so anyway, pressure, PSI is how we usually measure it. But the measures that we'll use in this class are ATMs, which are atmospheres. So 1 atmosphere is the pressure that the Earth's atmosphere exerts on the Earth. We'll also use a measurement called millimeters of mercury, or torr. I believe this is used in blood pressure measurements, right? And this comes from mercury in a tube. It's called it's an instrument called a manometer. You put mercury in a tube, you put it kind of underwater, and then the air pressure or whatever pressure you want to measure, pushes the mercury up, and however many millimeters it pushes it up, that's your pressure. So the more it pushes it up, the more millimeters it pushes it up, the higher the pressure.
Let's use it for O2.
For what? For O2 pressures? There's also inches of mercury. So same thing, except inches instead of millimeters. That's used in barometric pressures. Like if you check the weather or you see a weather report and they tell you about the pressure is like 29 point something and it's falling or it's rising, which has impacts on whether it's going to rain or not or snow. That's usually reported in inches of mercury. And then there's the actual technical unit in the metric system, PA, which stands for pascals. So just like any other thing, these all measure pressure, and we can easily convert them if we know the right numbers. And of course, I'll give you those numbers if you need them. Let's just look at the numbers now so we have a sense of what they are and, oops, spot here, and how big some of these are relative to the others. So we'll start with the atmosphere. Standard pressure of 1 atmosphere, which is the pressure the Earth's atmosphere exerts on the Earth at sea level. So that's one pressure measurement. Is 760 millimeters of mercury, which is also 760 torr. So nothing different about those. If you see either one, they're the same thing. And then that's 101,325 pascals. So those are really tiny. Which is 29.9 inches of mercury and 14.7 psi. So these are all called standard pressure, just standard based on that atmosphere. That's atmospheric pressure at sea level. You don't have to memorize these numbers. I'll give you these numbers if you need them. But it gives you a sense of what pressure amounts are. So pressure can vary by quite a bit depending on where you go. How does the air pressure change at altitude? If you go up high, what happens to air pressure? Goes down. Why?
Not as much oxygen.
Yeah, well, it's not just the oxygen. There's not as much atmosphere because some of it is below you. So only the part that's above you is pushing on you. So if you go up to like Denver, then your atmospheric pressure goes down to about 630 torr, which is absolutely noticeable for those of us who live at or near sea level. I don't know if anybody's ever been to a high place like that, but you definitely,
I didn't notice it.
yeah. You didn't notice it?
The one hiking up the mountain. I didn't notice it when I went to the very top.
Really?
Yeah.
I wonder if it's just because you kind of went up and went down, but if you actually like spend time,
Like, I kind of walked
yeah,
kind of slowly, so maybe that's why.
maybe. Well, if you go to Denver, just like going to the city, it's amazing how like you walk down the street and you're winded and you just feel like you're in terrible shape.
Pounding headache.
Yeah, and you get headaches. All right, so anyway, that's pressure. All right, so now let's talk a little bit about the relationship between some of these measurements of pressure. And then we'll go into why that is and how we explain it using atomic principles. Actually, before we do that, let's take a break because we're trying to, because we need to clear the minds a little bit. So let's take about 13 minutes. We'll come back at 7 and talk about the relationships of pressure, volume, temperature.
At the top of the mountains, you can keep water like forever and it will never boil.
That's not entirely true, but it takes a lot longer.
Oh, okay.
It takes a lot longer. Yeah, because of things that we'll talk about. So
So we need to go spread it back the more and more mass.
that's all those calculations. Yeah.
So when is our next exam?
A week from Monday.
The exam's next Monday.
Not the very next Monday, but the Monday after that.
So in 2 weeks,
2 weeks.
the 30th or something, 28th.
27th. Yeah.
So, oh, it was this Monday.
I don't think so. Check the syllabus, but I don't think so. It'll be like the last time.
They used to open book to save half of your classes, right?
You could have added some just like regular number equations that already know, so we can just do the equations.
Yeah, of course. It won't all be like that.
You give half points, quiz if we at least did, stuff's right.
Yeah. I mean, as much as I can.
You like half points right in your name.
No, you don't get that sort of name.
There wasn't a good one.
Hey, it's me. How's it going? Are you guys like super busy right now? Really? After I left, what was the turnout? After I left, what was the turnout? Really? Shit. That's awesome. Mira and Lauren pissed when not there. Alright. Right, I'm on break right now with my class. I could leave if you guys need me to, but I would prefer. Really? Are you sure? All right. Thank you so much, Emily. I appreciate your help. All right. Yeah. Especially. Yeah. There's bombs that I can test or whatever it was. Yeah. Yeah. There's something good. All right, sweet. Thank you so much. I appreciate it. And did Megan give you that pack from Janarda? Okay, no problem. Don't worry about it. All right, perfect. Thank you so much. I'll talk to you tomorrow. Are you in tomorrow? You're off? Okay, sweet. Then Friday, sweet. I'll talk to you Friday. All right, bye. Super rude.
Break, you do it on good.
Did we turn our lab from last Monday?
3 days ago?
No.
Last Monday, yeah.
Fuck. When did we turn that in?
Before lab, 2 days ago.
Before, like on Wednesday? A week ago, today?
No, today's Wednesday, on Monday.
Oh, so this past Monday?
Yeah, that's not Mondays, right? That's last week, yeah.
Yeah.
Give it to me, see if you got it. Or do that.
I wasn't sure if we turned in our lab on Monday or today, but that was from not this past Monday, but
Oh,
Monday
yeah, I
prior.
gotta,
Do you want us turning in? I know pre-labs are
do that to
due
do, and then
before the actual lab, but then the
The-
lab itself,
the lab
because
itself from the previous week is also due. So
on that Monday?
right at the beginning of the lab.
Okay. I turned in the lab on Wednesday. Oh, I think that was when you were said, when we had that sub, for that Monday,
That was the exam, right?
yeah, the exam. Then on Wednesday, you came back and collected
Right.
the
Right.
labs from the Monday prior.
Right.
So I think that threw me off.
Okay.
I just found my doctor who worked for his wife, he just told me this today, is a neuroscience, like, chemist, is that what it's called? Chemist,
Okay, like in
professional
That's not a
chemistry.
crazy ass
Yeah.
No, she's a freaking stay-at-home mom because her husband's a plastic surgeon,
job. Oh, really?
but she is brilliant when it comes to chemistry. And we had this like huge ICD-9 book for like diagnosis and everything. It's so big, it's a Bible. And he goes, "Oh, you're in chemistry? Oh, my wife tutors that. She, yeah." And I threw her down this big ICD-9. What? I was so pissed. But damn it, Bradley. Call me by his first name.
What were we gonna say?
I was pissed the rest of the day. I really made me mad. So, she was like every day. Ask me how much she charges me an hour.
All right, everybody feel refreshed? Ready to come back and do some chemistry? Oh, you're plugging your phone in.
Oh,
Why are you just facing the wall over there?
There's one here in here. Oh.
Don't forget it when you leave, because that happens a lot. Yeah. All right, let's look. I was wondering about, I don't know if this is something you've experienced, but it seems to me that, like, in my classes, a lot of people have broken phones. Like, a lot. What do you do to your phones?
I just dropped mine.
Mine is not broken.
Okay.
It's not.
College
Good.
is the best of them.
The what?
I just dropped mine and then I just kept dropping it.
No, some people don't
And then
like to
the
keep them in
bottom
the
fell out.
cupboards. Yeah, no.
Yeah,
Like if you drop mine, it won't break.
Yeah, I got mine. Yeah.
I'm
Okay.
not saying anything because I don't want to jinx it. I've had mine.
Oh, you don't. Yeah. Hey, all right. Anyway, I'm glad you got a new phone. Let's talk about relationships of gases. Let's remember, try to remind ourselves of what we saw on Monday. Yeah, all that kind of stuff. So first thing is the relationship between pressure and volume. And this is probably the easiest one, not the easiest, but most obvious. If you compress something, what happens to its volume? If you increase the pressure on something, what happens to its volume? It decreases because you're making it smaller, right? So like you take a balloon, you pressurize that air, the balloon gets smaller as you exert pressure on it. So we can say that an increase in pressure leads to a decrease in volume. And it works the other way too. If we decrease the pressure, the volume should increase. What did we see on Monday that showed that? Do you remember? Yeah,
I don't remember what it was called, but
we had these deflated balloons in a bell jar, right? Is that not what you're talking about? Yeah, but we decreased the pressure, keeping the volume or keeping the temperature constant, and so the volume of the gas in the balloons got bigger. Right. The way we express this in math, we're not going to do the math, but we can say that pressure times volume is constant. So the pressure multiplied by the volume is always going to be the same number, which means if one of them goes down, the other one has to go up to compensate. That's known as an inverse relationship. One goes up, the other one has to go down. One goes down, the other one has to go up. Another way this is sometimes written is P1V1 equals P2V2, meaning if you have a certain pressure and a volume and you change one, the other one has to change so that the product of the two is still the same, is still constant. But for our purposes, the important thing is to remember the relationship. What happens when you increase pressure or decrease the volume? You can also word it the other way. You can decrease the volume and then the pressure must increase inside. This is known as Boyle's law. So if you hear that, that's what it refers to. There we go. Another example of Boyle's law that we saw on Monday and that we see all the time is breathing. We talk a little bit about how breathing works, right? When you go to take a breath, you are changing the volume of your chest cavity. You're increasing the volume. So according to Boyle's law, if you increase the volume of your chest cavity, what happens to the pressure inside your lungs? It goes down. If you increase the volume, you decrease the pressure. And that lower pressure allows the higher pressure air from the atmosphere to rush in. And that's how you breathe. Then when you're going to blow that air out, you decrease the volume in your chest cavity by pushing your diaphragm up and increasing the pressure, which forces the air out into the lower pressure surroundings. All right, so that's Boyle's law. So now let's talk about another relationship we saw, probably the most spectacular from Monday, which is temperature and volume. How does temperature affect volume of a gas? Yeah. If you decrease the temperature, do you decrease the volume or you increase the volume?
We would decrease the volume.
Right. And what did we see that did that on Monday? Right. The balloon, when we cooled it with liquid nitrogen, we cooled the air inside that balloon and the volume got much, much smaller. So here's our warm balloon. And then we poured cold liquid nitrogen on it, and then it became a very flat, cold balloon. Right? The air inside was very cold, and the volume, the amount of space it took up, decreased. So a decrease in temperature, 2, and 2 O's. Yeah. Decrease in temperature leads to decrease in volume. We call that a direct relationship, meaning one goes down, the other one has to go down. The other way, the way kind of math way we would write this is V over T is constant. So you've got a fraction. If the top gets bigger, the bottom has to get bigger to compensate. If the top gets smaller, the bottom has to get smaller. If the bottom gets bigger, the top has to get bigger, and so on. So they have to balance each other out. This is known as Charles' law. And another place that we see that, so it's obvious when we cool things or heat things and they heat up, right, and they get bigger, or we cool the balloon and it gets smaller. It also works the other way. If you change the volume, you change the temperature. An example of that is like refrigeration. Anybody know how refrigeration works? How your refrigerator works, or your air conditioner? You know, never took
Electricity.
that apart. Electricity, sure, powers it. So what happens is you've got this fluid called Freon, and the fluid runs through some tubes. And then what happens is it expands. So it's under very high pressure, and then it expands or takes up greater volume. And that expansion lowers the temperature, and that's responsible for the cooling. And then you need a compressor, which is the thing that the electricity is actually running, that compresses that gas back into the little tube. Run through the little tube and then expands. So it's the expansion of gas that drives that cooling by lowering the temperature. And there's other parts to it too, and it condenses and does other stuff, but we can say that is a approximation of what happens.
Blue. Like because my air conditioning unit, like we took it apart, it broke.
Yeah.
And the apt guy, or
Mm-hmm.
no,
Sure.
no, I don't know, had his flashlight and he like waved it, and I thought it was radon. Is that they find in basements or something?
Radon?
Radon. I thought he was talking about radon. I
Oh,
said, "Oh, isn't that like really, really bad?" He goes, "No."
no, you're right.
Yeah.
Freon, yeah, Freon, the stuff, it's not actually colored, but they usually put a fluorescent dye in it so that if there is a leak, they can find it with a special light. Yeah. Right, radon is bad. Freon's actually bad too. It's bad for the environment. I don't know if anybody remembers, but a couple decades ago, all the cars switched over from one kind of air conditioning refrigerant to another kind, because the first time was responsible for the holes in the ozone layer in the southern hemisphere, and the new kind doesn't do that as much. So yeah, it's not great stuff, but it works. All right, so then the other relationships that we have are pressure and temperature. What did we have on Monday that showed a relationship between pressure and temperature?
The little like ball thing that you put in water.
Right, is that what you're talking about the first time?
Yeah.
Okay, I didn't quite get the motion. I thought you meant the bell jar thing, but okay. Yeah, the steel ball, the pressurized steel ball with the gauge on it, we put that in cold water, or in hot water first. What happened to the pressure?
Yeah, went up.
Yeah, went up. So pressure and temperature are also related. Then we put it in the cold one, and the temperature went down. Directly related. Yeah. If we increase the temperature, we also increase the pressure. Also named after its first describers. Right. And we write this, since it's also a direct relationship, one goes up, the other one has to go up. One goes down, the other one goes down, just like the temperature and volume. So we've got pressure over temperature is constant. Always stays the same. So if the bottom gets bigger or smaller, the top has to get bigger or smaller to compensate at the same amount. When we do calculations with these, it's important that we always keep our temperatures in kelvins. or it doesn't quite work out because the other ones don't start at 0. The other scales don't start at 0, but we're not going to do these calculations. We're just going to deal with it this far. So we're almost done. We got our relationships between our 3 main things, volume, temperature, and pressure. The last one is just the amount of gas. Amount of gas. And that should be pretty clear. We'll do it with volume. So if you have more gas at the same pressure, what happens to the volume? Yeah, it goes up, right? You put more gas in the balloon gets bigger. Pretty straightforward. The way we actually word that, it's called Avogadro's law. We say an increase in moles of gas leads to an increase in volume, or V over N is constant, N being number of moles. So you can actually use this to do some calculations to actually figure out how much gas you have just based on pressure and volume and temperature. So if you know pressure, volume, and temperature, you can determine the number of moles of gas. And if you know any other combination of those, you can determine the one that's missing. Again, we're not going to go through all that math, but it is important that we keep in mind these relationships. So the next part then is to explain the relationships. So if I asked you, why does an increase in pressure lead to a decrease in volume? We haven't really talked about that, right? We haven't talked about the why. We've just talked about it does. And because Boyle said so is not really a reason. So we really want to look at what's going on with the molecules, what's going on with the gases to explain these phenomena that we see. Do you remember really early in the semester we talked about the difference between a scientific theory and a scientific law? You remember that? No? All right, let's review it. Anybody remember what that difference is? Why it's important?
Did we talk about it?
We did, but probably briefly.
When you just think of the laws, like that's not what a theory is.
Yeah, that's kind of the popular explanation. And in fact, when we discussed this, I said, that's not right, but we're going to come back to that because it's so ingrained in our heads that law is like a fixed thing and theory is a changeable thing. That's actually not how it works at all. Law is a set of observations. So this happens and this happens. This happens and this happens. That's why this is called Boyle's law. Pressure changes, volume changes. Volume changes, pressure changes. That's an observation. It doesn't tell us anything about why or what causes it. It's just, this is what happens. So that's a law. A theory, a scientific theory, deals with the reasons behind that law. Why is it happening? Yeah, and actually both require evidence to support them before they're accepted, and both can be disproven in the same way if enough evidence comes to the contrary. So, like the atomic theory, the theory that all matter is made up of atoms, I mean, that's well settled. We can pretty much see atoms now. There's not a whole lot of people that will argue that stuff is not made of atoms. But it's still called the atomic theory because it doesn't have anything to do with how right it is. It explains something. It explains how matter interacts with each other by saying that it's made up of atoms. And so that's considered a theory. So if you're explaining why something happens, that's a theory. If you're stating observations, that's a law. So you got that difference? So all of these things are laws. They're just, this is what happens. But nothing about why that happens. So what we're going to talk about now is the why. And the why is called the kinetic molecular theory of gases. And using this theory, this set of rules of what gases are like, allows us to predict what's going to happen in all these different laws and to explain them. And so a powerful theory is predictive. It allows you to figure out or make a good guess about what's going to happen without even doing the measurement. And then you do the measurement and the experiment confirms the theory, and that gives it even more evidence. All right, so there's 5 parts of the kinetic molecular theory. You don't have to like memorize every one, but I'm going to show you how to use them to explain these other things, and that is something that you'll have to be able to do. So first, we'll write this together. I'll try to write slowly. Gases consist of small particles, right, atoms or molecules, that move randomly with high velocities. So we're going to say, okay, gases are tiny particles moving in all possible directions randomly, really fast. That's an important assumption of the theory, because if the gases are all going in the same direction, that may not explain stuff well. If the gases are moving slowly, that doesn't really work either. So we're going to have to assume that they're going fast and that they move randomly. So far, so good. The second part is the attractive forces between gas particles, so atoms and molecules, are very small and in fact negligibly small. So we're saying that unlike in liquids and solids, the molecules don't really associate with each other. The molecules are on their own, and what this means is that when they hit other molecules, they're not really going to stick together. They're going to have what's called an elastic collision, which means when they hit each other, they will bounce off with exactly the same energy that they started with. So they're not like sticking together or anything. It's just colliding and going all over the place, kind of on their own. Third, the actual volume, let's say occupied by, the gas molecules or atoms is tiny compared to the volume the gas occupies. What does that mean? That means that if you have a 1 liter balloon filled with gas, that gas is taking up a liter, and we say that that is a liter of gas. The volume of that gas is 1 liter. But the actual space that the particles take up is almost nothing. I mean, it's there, they're particles, but the actual space they take up is almost nothing. So most of any gas is empty space, but it fills whatever container it's in, which means if you have a liter of gas in a balloon, but then you compress that balloon to half a liter, you now have half a liter of gas. This is what makes gas compressible, is that most of it is empty space. So you can push the molecules together, they're still taking up way more space than the actual size of any individual molecule. All right, and now probably the most important part in terms of the explanations. Well, the next two are kind of the most important parts. Gas particles are in constant motion moving rapidly in straight paths. So they're always moving, and they're always moving straight. Why is that important? That means that at some point, every molecule in a sample of gas is going to collide with the walls of the container. So if they're moving in straight lines, eventually you're going to hit the wall, right? We all run in a straight line, somebody's going to hit the wall. That wall hitting is what we call pressure. Collisions with the container walls is what we call pressure.
Is that the fifth one, or is that?
This is part of the fourth one. So this is this consequence of this constant motion, is that we now have something we call pressure. So whenever we talk about an increase in pressure, what we're saying on a molecular level is there are more molecules hitting the walls, or they're hitting the walls more, the same amount as hitting the walls. Anyway, an increase in pressure means an increase in collisions of the molecules with the walls. That's what's so important about this one. And then the fifth one the average kinetic energy of gas molecules is proportional, meaning it varies with the Kelvin temperature. So if something is always in motion, right, that means that your kinetic energy is that energy of motion. Kinetic energy can be described as how fast something is moving, multiplied with how big it is. So from a math standpoint, for those of you who like that sort of thing, which I assume is all of you, if you haven't taken physics, kinetic energy, the equation for kinetic energy is 1/2 mv squared, where m is mass and v is velocity. So if something's faster, it has more kinetic energy. If it's bigger, it has more kinetic energy. So a big thing and a small thing moving at the same speed, the bigger thing has a greater kinetic energy. Two small things, whichever one's moving faster has a greater kinetic energy. That's what that means. So that means that an increase in the Kelvin temperature is going to increase the speed of the gas molecules. Okay, that's it. So that's the 5 parts of the kinetic molecular theory. So now let's talk about how, we'll leave this up here, and let's talk about how this explains, let's start with the volume or the pressure and temperature one, the last one, where we dip the thing in the cold and hot. So we said when temperature increases, we put that thing in the boiling water, pressure increases. And the question is why? Well, the answer is not because that law says so. That's never a good answer. The answer is, well, an increase in temperature leads to an increase in kinetic energy of gas molecules, which means they're moving faster. If they're moving faster, they're colliding with the walls more. And wall collisions mean pressure. So when we increase the temperature,
We increase pressure.
we increase the pressure because the gas molecules are now colliding more with the walls.
And it's proportional.
And that's a reason behind that. That's how the theory explains the law, explains what we see. Let's try another one. Let's look at, yeah.
Is it something that happens like, let's say in human beings, like when it's so hard, even your feet, like when you wear your shoes, there's some shoes that feel kind of tight, but in the wintertime, you find your feet not loose or something.
That's a good way to remember it. It's not quite the same because that has to do more with the fluid in your body.
Water retention.
Like
That's
in
why
the
it's
summer,
different.
you have more fluid and it's going down to your feet. That's what's causing that. It's not really gas related. But it's the same trend. So if that's how you want to remember it, then yeah, absolutely.
Wait, what happens when?
Water retention in the summer is common.
Yeah, water.
The body
You get more
retention-
water in your body, so you have more fluid in your body. So that makes everything kind of bigger.
Or
And-
something?
And so when you're sitting, the water goes down to your feet get bigger. Or when you're walking, just from gravity, and then your shoes don't fit as well.
I have a question, not that it's like, when you fly in an airplane,
Mm-hmm.
I noticed taking a picture like while you're like in the air, your face looks, I don't know, like more, not swollen, but when you land, you kind of, your fingers, your digits are more swollen. I don't know, is that because of the pressure you were such and such height?
I think it's more because of the couple things. The cabin pressure, like the fact that the cabin is pressurized, and just that you're sitting for that amount of time. That's why people sometimes have issues with blood clots and things like that on planes. I think it's more the sitting.
Is that why pregnant women's like feet, like
Fluid, yeah. They just have a lot more fluid. Yeah. So if we go back now,
One
Yeah.
question. She reminded me of something, like with the pressure in altitude,
Uh-huh.
as far as flying is concerned, is it the reason why people have jet lag after flying? Maybe one of-
No, jet lag comes from a change in time zone. So you're somewhere where it's nighttime and then you fly and then your days and nights are messed up and it takes your body some time to get used to that. That's what jet lag comes from. Yeah. So anyway, this is what we just explained then, the Gay-Lussac's law. We talked about how we can explain that. So this is the law that, by the way, that describes about your tires. So your tire looks a little bit low in the morning and you think, well, I'll check it again when I get to school. So you hop in, you drive to school, and then it seems fine. Well, the reason is that the temperature went up because driving on it warmed it up, and the increase in temperature leads to an increase in pressure, right? So now it's pressurized. All right, so let's look at another one. How about Avogadro's law, as long as you have. Increase in moles of gas leads to an increase in volume. How can we explain why that is using this idea of collisions with the walls and speed of gas? So remember, if we're dealing with volume and number of moles, that means that pressure and temperature need to stay the same. So how might you explain what's happening here in terms of the molecules colliding with the walls?
Yeah.
So there's more of them, so what does more mean? Well, but remember, they're traveling in straight lines. So if you have more of them, they need to bounce off the walls more.
Yeah.
Okay, but then pressure is constant. So that means that the size of the container has to change to accommodate that.
But in Avogadro's laws, moles of gas is the same as increase in volume.
Mm-hmm. So you can think of moles of gas as like amount of gas. So imagine everybody in this classroom gets up and starts running randomly fast in straight lines, and you're going to collide with the walls in certain
that's
points.
even weirder.
Yeah, so you're going to hit the walls, and keep going, hit the walls. Let's say 20 more people come in. Suddenly, you're going to have a lot more collisions if everyone's running around, right? So if pressure stays constant, that means we need a bigger room if we want the same rate of collisions with the walls. So that's another way of saying the volume has to get bigger to accommodate the increase in particles without changing the number of collisions. pressure held constant means the number of collisions has to stay the same. So if the number of collisions has to stay the same, we need a bigger room to get everybody in there colliding at the same.
What about like, could you relate to the soda can? Because there's technically gas in soda
Yeah.
and there's volume because of the liquid. When you open the soda can, there's a release of pressure.
Sure. Because some of the gas has escaped. So it's kind of like instead of volume, it's like this with pressure.
Okay.
Which is another relationship. We didn't look at it, but it's another relationship. You could put a P in place of that V, and that's kind of what you're describing. All right, let's look at that in terms of Boyle's law here. So pressure and volume. How do you explain the relationship between pressure and volume using this idea of collisions of particles that we talked about? Don't worry, we still got some time. You want to give it a try? Yeah, how do you explain this relationship between pressure and volume? So here's an observation. Pressure changes inversely with volume. How do we explain it? How do we account for that? If somebody said, why does this pressure keep changing when I change the volume? How can you explain that?
Like the first one is the gases versus of some particles and random at high.
Yeah. So how does that explain this? How do any of those ideas and those 5 things explain the observation that we see here?
Because of the high velocity at which the gases made. If you compress with the compression, it's very easy for it to easily come together,
Mm-hmm.
and the increases the volume of the how do you call it?
Container?
The gases.
Okay.
Kind of like burping. When you
How like burping?
let out a burp, pressure, you don't feel as bloated anymore. There's a decrease of volume or just bloating.
Okay.
Right?
Yeah, I think so.
Because it's a small amount of gas
But
in your
but
body,
again-
and it's releasing.
But that's an example. That's not a reason for the phenomenon on the molecular level, right? That's saying, well, here's an example of this relationship.
Okay.
Well, okay, so let's go back and think about what are we looking for? We're looking for what happens when one of these things changes. I think this one's easier to see on the volume side. So once again, everyone is running randomly at high speed in straight lines in this room, smashing into the walls occasionally. If the volume changes, so if the room gets smaller, are you going to collide with the wall more or less? More, right? Yeah. And so if those collisions are the pressure, you've just explained an increase in pressure. So if the container gets smaller and the gas is moving at the same speed, it's going to have more collisions with the walls. More collisions with the walls means more pressure. We can think about it the other way. The other way is a little bit weirder to think about, but an increase in pressure means what in terms of collisions? Means more collisions, right? So an increase in pressure is more collisions. So everyone's running around the room. And if we're hitting the walls more, but we're not running any faster because the temperature is staying the same, well, then the room must be small, right? So that shows the same thing. If we're increasing the pressure, we're hitting the walls more, but we're not running any faster, then the room must be smaller, the volume must be smaller. The only one we haven't looked at yet is the temperature and volume, but we can look at this in the same way. Like we did with the balloon, what we could say is, when we poured that liquid nitrogen on the balloon, we decreased the kinetic energy of the gas. So the gas has less energy, which means the gas molecules are moving much more slowly. If they're moving much more slowly,
there's gonna be a decrease in temp, there's an indication that there's a decrease in temp.
Right, so we decreased the temp, we made them move slowly, and that led to a decrease in volume because now they couldn't collide with the walls quite as much, right? And so if we wanted to keep the same pressure, because have atmospheric pressure basically, we needed to change the volume, decrease the volume to accommodate that. Right. So those are the sorts of ideas that I want you to be able to do with these, not only to remember the relationships, like just by rote, but be able to think through them. So if you have a good handle on this, you shouldn't need to remember what every particular formula or relationship is. You should be able to say, okay, well, what happens if the pressure decreases? If the pressure decreases, that means we're hitting the walls less, so that means whatever. Yeah.
When are we gonna have this over?
Let's do it next week.
Quiz on this,
Yeah. Actually,
this could be the high quiz score that's gonna replace maybe 5 of my
let's see how much more we've got to talk about in this chapter before we commit to that. All right.
The chapter is this.
Most of the chapter is this.
I have a question.
Yeah.
When you're talking about the relationships
Mhm.
between temperature and volume, V over T is equal to K. Are you referring to Kelvin or?
Nope, just referring to
constant?
some constant, some number. That
Okay.
that little k just means some number.
Okay, okay,
That has to always equal some number.
okay.
Why is it
It could be C if you like.
security?
K is a
I was
common-
trying to figure out because I know it's
Yeah,
common.
K I think it comes from probably German, but K is like the standard constant for stuff. But C is sometimes used also. So yeah, C is fine. All right, one last thing we need to talk about then, and that is partial pressures. So this is the only math in the chapter. But you gotta have a little, right? So with liquids, we can talk about their volumes. With solids, we can talk about their masses. Neither one of those really tell us what we need to know when it comes to gases. And so partial pressures deals with a mix. So like if you mix two solids, it's pretty straightforward. You take so many grams of this, so many grams of this, you mix them together, and now this mixture contains such and such percent this and whatever percent this. With gases, it's usually not practical to measure them by mass. They have mass. They're made of particles. They're made of matter. They have mass. But measuring the mass of a gas is often difficult, as you can imagine. If you want to measure some gas, you have to measure a balloon and then put it in the balloon and then weigh the balloon with it in it and all this stuff. So we often measure it by pressure instead because it's just easier. And the way we can do that is by combining gases, we can just add up their pressures. So let me pull up this picture. I'll just draw it. No, I'll pull it from the book. It's going to look terrible if I try to draw it. This is page, if you've got your book or you're following along, this is page 272. 6 in the old book, yeah, so it'll be a different page number. But the same picture is there, I know. Yeah, it's like the exact same thing. It's nice the internet works a little bit better around here at night. Not many people around like watching movies and stuff. All right. So here's a couple gas tanks. Helium and argon, two gases, two noble gases. So you got helium at a pressure of 2 atmospheres and argon at a pressure of 4 atmospheres. If you mix that together, you'll have a tank that's total 6 atmospheres of pressure. So 2 atmospheres from the helium, 4 atmospheres from the argon, 6 atmospheres total. So the total pressure can be thought of as the sum of 2 partial pressures. So that's our total pressure. These are called partial pressures. So the partial pressure of helium, the partial pressure of argon. And the important thing about that is that not only can we now figure out the partial pressure of an unknown gas, but these are proportional to moles, which means, let's say the helium here, the helium, partial pressure of helium is 2 atmospheres. In a total pressure of 6 atmospheres, that means that this thing is like 1/3 helium, 33% helium by mole. So the mole fractions, or the amount of moles of one versus the other, can be measured just by knowing the pressures. So here's an example from the book of how you might calculate a problem. Oops. Here. Of a problem that you might be able to calculate based on partial pressures. And we'll do some conversions here too, so we can practice that. Anybody do any scuba diving here? Scuba diving? Yeah, me neither. But if you did, you would need to get, tank and all that stuff. And if you're going really deep, more than 200 below, you actually need a special mixture that's mostly helium, or a big part helium, because the nitrogen can give you something called the bends when you come up, if there's nitrogen. So you use a special mixture of oxygen and helium if you're really diving deep. And this problem is saying that at the depth, wherever they're going, the total pressure of the gas is 7 atms. If the partial pressure is 1140 millimeters of mercury, what is the partial pressure of the helium in the breathing mixture?
Will you just divide the total depth, 1140?
The pressure of oxygen?
Yeah.
Well, yeah, what we need to do is just subtract the partial pressure of oxygen from the total pressure. The only problem is they're in different units here. So first we've got to convert our millimeters of mercury to atmospheres so they can be in the same units. So we've got 1140 millimeters of mercury, and we put that one on the bottom because we want to get rid of it, and we put atmospheres on the top. We look up that conversion, and we find that there are 760 millimeters of mercury in 1 atmosphere.
Wait, is that 760?
Yes. And that comes out to 1.5 atmospheres. Okay, so now we've got stuff in the same. That was the partial pressure of oxygen. We got it in the same units. So we've got a total pressure. Remember that the total pressure equals the sum of the partial pressures. So that's the partial pressure of oxygen and the partial pressure of helium. If the partial pressure of oxygen we now know is 1.5 atmospheres and the total pressure is 7.00 atmospheres, what's the partial pressure of helium have to be? Oh, so if the total pressure is 7 and the partial pressure of oxygen is 1.5, what does the partial pressure of helium have to be?
Subtract that
1.5
Yeah.
or
1.5.
Right.
but where did you get this 760?
Oh, I would give you that conversion, but it's from up here. I just happen to know that one. 1 atmosphere equals 760. So the partial pressures have to add up to the total pressure. If one is 5.5 or 1.5, that means the other is 5.5. So this tells you how much helium you need. So you could calculate, if you had a tank of helium, you could figure out how to put 5.5 atmospheres into the tank with the 1.5 atmospheres of oxygen and have the appropriate total pressure. And this is in fact how they would do this. They would calculate how much oxygen you need and then figure out how much the rest needs to go in based on the partial pressures. You'll also see that something like if you have nitrous oxide in your dentist, it's like a gas that they, laughing gas, kind of makes you relaxed and have a good time. But that's not just pure nitrous that's going into your nose, it's a nitrous and oxygen mixture because you need oxygen still. And so those are measured again by partial pressures. You've got gases, you've got a total pressure, whatever they want the pressure to be of the gas, and then it's going to be partially oxygen and partially nitrous oxide, and you can calculate which one's which. Excuse me. Right. The book also has an interesting thing you should read at the end about how partial pressures influence blood in your body. So when oxygen transfers into your blood in your lungs, that is a pressure differential. And so you can calculate based on the partial pressures whether the oxygen will go in or the carbon dioxide will go out. The carbon dioxide has a lower partial pressure than the oxygen, and so in oxygenated blood, and so it goes out and the oxygen goes into the blood.
Is that like in osmosis?
Yeah, right. We'll get into that when we talk about solutions next. All right, so I think that's about it. That's all we're going to talk about gases. So it's the relationships, the reasoning behind the relationships, and the partial pressures. You can skip everything else in that chapter that talks about how to calculate pressure, volume, temperature, all that stuff. And this should be an easy quiz then? We'll throw a reaction in there too, just so you can practice that again too.
Like extra credit?
No, like part of the
Extra credit
quiz.
for 10 points to make up for that quiz.
Remember, the more quizzes we have, the more.
Can we have 2 more quizzes like this?